Good morning, everyone. So here is our video on rates of change, but specifically, we want to start talking about the derivative in an application sense. So far in class, we've worked with the derivative really just on a graphical basis and as a function. We haven't really put any sort of like real world scenario to it. And so that's what I want to start to get into today because I think it's really going to help us continue to develop our understanding of the derivative and really what it can be used for. So, what we know about the derivative, right, is that it is how much something is changing. It's the instantaneous rate of change at a singular point or a singular moment in time. A couple of things that we can start talking about or just start to think about just rates of change in general, right? Is how fast the car is moving, right? Something like miles per hour, maybe how slowly an ice cube is melting, the velocity of a particle moving in space, which has this physics connection, which we'll get into today actually a little bit. All of these things are rates of changes, right? The rate at which a particular scenario or a particular process is changing. But here's this language that I talked about yesterday a little bit. Um, all of these things are changing with respect to time, typically. So most of the application that we do is going to be with respect to time. As time changes, what is happening with this process? How much is an amount changing? How much is the speed changing? And all of these things are measured with respect to time per hour, per minute, per second. As soon as we see that language, that per hour, that per minute, anything like that, we know that we're now in a rate of change. You can think of those almost as a derivative, or at least the language of derivatives. Anytime you see that type of language, we know we're talking about the derivative itself. And so here's what we want to start talking about today. We're going to go through a couple of things. The first major application that we're going to look at, and we will see a lot more of this as we move forward through the year. This is just an introduction into particle motion. Particle motion is one of, I think, the easiest ways to start to get a handle on how the derivative can be used within application. And you'll start to see words like velocity, speed. Eventually, we'll see acceleration and how all this plays in. Today will be a very sort of just basic foundational level problem for particle motion. But I think it's a nice first step. All right. But in general, when we're talking about problems, specifically application problems that deal with rates of change, we always start with either a position function, which we'll see in the particle motion, or what I'm going to call an amount function, right? So the amount of something that is currently present or that is present over time. And we want to take the derivative of all of those functions, and then we can analyze the rate at which that process or the particle motion is changing. So basically what we're going to do is we will always start with some type of amount or position function. And at least for this first half of the year, we will take the derivative of that function, usually plug in some type of time value, and analyze what that computation gives us. Okay. So here is the first example of a particle motion problem. And again, this is a very, I'm going to say like a foundational level particle motion because we're only moving in a very strict space and for a very sort of simplistic function based off of what we know in terms of how to take the derivative. So here's the scenario. This particle is moving back and forth on the x-axis. So picture the xy coordinate plane and a particle, a small particle that's just moving back and forth on the x-axis. It's not going up or down. It's not going sideways. It's not going on a curve. It is just literally moving back and forth on the x-axis. You can go left, you can go right, but that's it. The position of the particle is modeled by this function, x of t equals 5t squared minus 20t plus 9. That means that for whatever time t, whether it's in seconds or minutes or hours, this problem doesn't tell us that, and a lot of these particle motions don't, so that's okay. Whatever t value we plug in, we will get an output. Well, that output will be the x value that it is currently on as it moves through the x-axis back and forth, back and forth. So that's what that tells you. That's the position function of the particle. Plug in a t value, you get an x value out. That's the x value that the particle is currently at. What we want to do is find the velocity of the particle at t equals 1 and t equals 4. And then we're actually going to talk about what those values mean and how we can use them specifically in this scenario. So The velocity is one of the major applications of derivatives for us throughout this year. And so here's the question again. The very first big piece of information that we're going to learn with particle motion is that the derivative of a position function is equal to the velocity of a particle, or the velocity of really anything that's moving, right? So if you're in a car that's driving down the road, hey, you're at mile 1, mile 2, mile 3 at times t equals 1, t equals 2, t equals 3, and I were able to create some type of position function or position model. If I were to take the derivative of that function, I would know how fast the car is going, the velocity of the car. So this is one of the major applications of rates of change. Specifically for us, the derivative of position equals velocity. The good news is that we now know how to take derivatives of functions. And so if I were to take the derivative of the position function, x prime of t, which equals the velocity, or v of t, equals 10t minus 20, right, using the power rule, which we just found. Once we have the velocity function, we know we want to find the velocity at t equals 1 and t equals 4. So all we have to do is plug t equals 1 and t equals 4 into the function, right? So you'll see that over here. V equals 1 is equal to negative 10, and v equals 4 is equal to positive 20. And so I'm highlighting those positive and negative values because this is another big part of particle motion that I don't want us to get confused about. The negative and positive values do not tell us whether a function is speeding up or slowing down. We will have to analyze acceleration eventually along with velocity in order to know that. So big part, I'm going to write this down, right? The negative and positive values of velocity do not tell us whether a particle is speeding up or slowing down. What they do tell us is the direction of the particle. So if the velocity in this particular scenario is negative, so for v of 1, the particle is actually moving to the left or towards negative infinity at that moment in time. If the velocity is positive, it's actually moving to the right. So at t equals 4, we're heading towards positive infinity exactly at that moment in time. Okay, so there's a couple of really big things that have to do with particle motion. We know the derivative position is velocity. We know the velocity function will give us either a positive or negative value out. It does tell us how fast the particle is moving at that time, but more specifically, the positive and negative values tell us whether it's moving right or moving left. Okay, so the next big piece I want to talk about today, and this is actually our last piece, and then you'll have a chance to try some problems on your own, is we can analyze processes with multiple rates of change happening at the exact same time. All right, so think of any scenario, just in the real world where, well, typically rates of change are happening all around us, but there's not just one rate of change happening, right? So if you think about maybe a skydiver, right? Somebody jumps out of a plane and is skydiving. Well, yes, they are moving towards the earth at some particular rate of change, right? But what else is happening? They're encountering a lot of friction from the wind and things of that sort, right? So now you've got two rates of change, because how much is the rate at which the wind friction causing the skydiver to slow down, and how much is the rate at which gravity is pulling that skydiver down? How fast are they falling because of that? And how do those two things work together? And so this idea of analyzing a scenario and all the different rates of change that are happening at one time becomes really important for us. And it's a really good application that we can talk about. Okay. The example we're going to talk about, again, a little bit basic, but I hope that it gets the idea across, is the example of filling a tub with water. And what is at least one additional rate of change that I could add into that problem to help you sort of start to think about this idea of processes with multiple rates of change. So here's the scenario. Here's the setup. This is also a really good free response style question that you might have to do eventually. So this is a really good example for us to work through. So the scenario is that a tub is being filled with water. Okay. The amount of water in gallons being filled in the tub at any time t, where t is measured in minutes, is modeled by this function. W of t equals e to the t over 10 plus at squared, specifically for the values from 0 to 4, for the t values from 0 to 4. What we have here is that amount function. So remember, I told you this is like that either a position or an amount function, we know at any time t from 0 to 4, the amount of water in the tub is modeled by that function. So if we want to know how many gallons were in the tub at t equals 1, we would just plug 1 in for t. We would get e over 10 plus 8 times 1, right? So e over 10 plus 8, some random decimal. We're going to use our calculator throughout this problem. So if you don't have a calculator out, if you want to follow with a calculator, you might want to pause the video and get that out now. So we're going to go through a couple of different questions here, and these are really typical questions for this style of problem. And so I think this will be a really good model for us to work through. The first question, and this is a little bit different, right, is find the average rate of change of f of t from t equals 0 to t equals 2. The key word here is the average rate of change. So for part A, the very first thing that we want to talk about is average rate of change. We actually talked about this a little bit already when we used our football field analogy, right? We had said, well, the average speed was just distance over time. And really what we talked about, we sort of parlayed that into, well, that's just the slope formula, right? It's just my ending distance minus my starting distance divided by the time it took. And so whenever we see the words or the problem, find the average rate of change, immediately in our heads, we should start thinking about the slope formula. And more specifically, the slope formula as it pertains to this problem. So we know the slope formula is y2 minus y1 over x2 minus x1. Specifically for this problem, though, the outputs are in terms of f, right? That's my function. And my second x value is 2. My first x value is 0. And so for this problem, the average rate of change is f of 2 minus f of 0 divided by 2 minus 0, right? You can think of that as like a distance over time, or in this case, sort of a gallons over time scenario, right? How many gallons are at t equals 2? How many gallons are at t equals 0? And how long did it take to get from 0 to 2? So all we have to do in this case, we're actually not using the derivative yet. We're only using the function, right? So it's f of 2 minus f of 0. And that would give me this calculation. Just plug in 2 and plug in 0 into our original function. And then we get this answer. All right. Notice that the answer is a rate, though, right? It's in gallons per minute. The top function, f, its output is gallons. The bottom of the fraction, that's time, right? Time in this case is measured in minutes. So the answer is still 16.31 gallons per minute. That's how fast the tub is being filled on average from 0 to 2. All right, very good. Okay, so in my next problem, now we're getting into the derivative. Find w prime of 2, and using correct units, we want to interpret the meaning of our answer in the context of this problem specifically. So first thing we have to do is find the derivative. We know how to take the derivative of functions now, specifically of both parts here. We have an exponential piece and then a monomial piece. So we'll have to use our exponential rule and then our power rule to solve this derivative. Then all we have to do to find w prime of 2 is plug 2 into that derivative. And then we'll talk about what that value means. So if we were to take the derivative, here's what it looks like. Right? W prime of t equals e to the t over 10. That part stays the same, right? The derivative of exponential is itself, e to the x equals e to the x. So e to the t equals e to the t. If I divide that by 10, that stays as well. Plus 16t, 8t squared, its derivative, bring down the 2. 8 times 2 is 16. Subtract 1 from the exponent. 2 minus 1 is 1, so you get 16t. There we go. So now we have the derivative. We want to actually plug in 2. So 2, if I plug in 2, I get e squared over 10 plus 32. Again, using your calculator, you get 32.739 gallons per minute. Okay, 32.739 gallons per minute. The interpretation here is that at t equals 2, the tub is filling with water at a rate of 32.739 gallons per minute. So it's being filled at a rate of 32.739 gallons per minute. And there's our units as well. Okay, so the part C is really the heart of this problem. And this is this idea of looking at a process that has multiple rates of change and how we can analyze exactly what's happening. So here's sort of the twist in the problem, right? At t equals 3, a hole is punctured into the bottom of the tub. So if we have a hole that's punctured in the bottom of the tub, what's going to happen, right? Water is going to start spewing out or coming out of the tub at the bottom. However, there's still water being filled, right? Because the original model was from 0 to 4. The tub is still being filled with water while water is coming out of the bottom of it. Start to picture that in your head a little bit and kind of get an idea of what's happening here. What we know is that the rate at which water is emptying from the tub is modeled by the function g of t equals t to the 5 halves, where t is measured in minutes and g of t is measured in gallons per minute. Is the amount of water in the tub increasing or decreasing at t equals 3.5? We need to explain our answer, or explain our reasoning there. So here's the scenario. We've got water coming in. We know the rate at which water is coming in because we just found the derivative w prime of t. Right? In this next piece, there's a hole that's punctured in the bottom of the tub. Water is coming out. We're actually given a function, g of t, that is already a derivative because it says the rate at which water is emptying from the tub is modeled by g of t equals t to the 5 halves. And then even further, it tells us g of t is measured in gallons per minute. As soon as I know the output is gallons per minute, that's a rate of change. So I actually am not going to have to take the derivative of g of t. I just need to use g of t as if it was already a derivative. Now, how do I know whether the amount of tub in the water is increasing or decreasing? Well, think about this. If I have water that's coming into the tub and water that's coming out of the tub, how would the water level be rising? Or how would the water level be decreasing? Well, if the rate at which the water is coming in is greater than the rate at which water is leaving, well, then the tub's going to be filling up. If the rate at which water is leaving is greater than the rate at which water is coming in, then the tub's going to be emptying, right? So all we need to do here really is just analyze both of those values, see what the difference between the two of them is, and understand the analysis. So if g of t is already a derivative function, we're just going to compare g of 3.5, because it's already a derivative function, with w prime of 3.5. If g of 3.5 is larger, tub is losing water. If w prime of 3.5 is larger, the tub will be gaining water. So let's check it out. Let's see what happens. So if I use my two functions, w prime of t and g of t, I plug in 3.5 to both of those values. I get a rate of change for both pieces there. Again, you can see that using your calculator. And what I notice is that w prime of 3.5 is 35.312 gallons per minute, and g of 3.5 is 22.918 gallons per minute. Pretty obvious here that w prime is larger than g in this specific case. So what's going to happen? Well, since w prime is greater than g of 3.5, the amount of water in the tub is increasing. Or we can even look at it this way, right? Because if I were to subtract the two rates, that would also tell me what's going on. If w prime minus g is greater than 0, then the amount of water in the tub has to be increasing. If this was flipped, if w prime minus g was less than 0, then the tub would be losing water, or the amount of water would be decreasing. We would have a negative overall rate of change. This subtraction right here, if we were to think of this as w prime of t minus g of t, that would be what we would call the overall rate of change function for this scenario. I can understand exactly what's happening at any time t if I were to just put together those two pieces with subtraction. It would tell me exactly what's happening, whether the tub is increasing or the tub is decreasing. Okay, so that's actually it for the video. You will get, and it will be at the very beginning of class, you will get a worksheet with a few problems for you to try. They're very similar to the two problems that we went over today. I hope this helps give you a little bit better idea of what the derivative is and how it works. And please let me know if you have any questions.